So, have you ever looked at one of those incredible science images, the ones with tiny dots, and wondered how scientists can possibly know that those dots are individual atoms? And not just that, but what kind of atoms they are? Well, today, we're going to break down a technique that does exactly that. We're talking about a method that can basically weigh a single atom from a speck of dust that's older than our own sun. Let's dive in.
Okay, what you're seeing right here, this is pretty mind-blowing. This is a tiny piece of carbon found inside a meteorite that actually formed before our sun even existed. Yeah, it is literally stardust. And those little bright dots you see, each one is a single heavy atom captured by one of the most powerful microscopes on Earth, a scanning transmission electron microscope, or STEM for short.
And that right there, that's the big mystery we're going to solve in this explainer. I mean, how do you even begin to go from a black and white picture of bright dots to identifying the specific elements that were cooked up inside a star that died billions of years ago? Well, we're going to follow the clues, just like the researchers did, and crack this case together, step by step. Now, the secret to this whole thing is that the microscope is really clever. It doesn't just snap one photo. It actually captures two completely different but complementary images at the exact same time. This gives us two sets of clues to work with. You can think of it like getting a picture of all the shadows and another picture of all the sparkles, simultaneously. And the idea behind these two images is actually pretty easy to grasp. The first type, called brightfield, is basically a shadow map. It shows us where a beam of electrons got blocked. The second one, darkfield, is the complete opposite. It only shows us where those electrons got knocked off course, making them light up, kind of like dust floating in a sunbeam. So let's zoom in on that shadow image first. For a brightfield picture, the camera or detector sits right behind the sample. So anywhere the sample is thick or dense, it's going to block more of the electron beam, which casts a darker shadow. This gives us an amazing map of the sample's thickness and density. And now for the sparkle image. For the darkfield picture, the detectors are moved off to the side. They're only there to catch electrons that have been smacked way off course by hitting something. And it just so happens that heavier atoms, the ones with lots of protons in their nucleus, are way better at scattering electrons. So in this image, heavy atoms just light up like brilliant stars against a totally dark background.
So before we can figure out what those sparkly atoms are, we first have to map out the terrain they're sitting on. And to do that, we're going to use our brightfield image, that's the shadow picture, to build a super precise thickness map of our little piece of stardust.
Now, you can't just use this method on anything. It has some very specific needs. But the most important one, and maybe the weirdest, is that the sample actually needs to have a hole in it, a literal empty space. And that hole is absolutely essential because it lets the scientists measure the full, unfiltered power of the electron beam. That gives them a perfect 100% baseline to compare everything else against. The process itself is pretty logical when you break it down. First, they point the beam through that empty hole to calibrate its intensity. That's their maximum value. Then they scan across the actual sample and measure how much dimmer the beam gets. Finally, they use a formula that connects that dimness to the amount of stuff the electrons pass through, and they can calculate the exact thickness at every single pixel. And this is what they get, a perfect, detailed thickness map of the presolar grain. It turns out it's unbelievably thin. We're talking between just 4 and 7 nanometers thick. To put that in perspective, a single sheet of paper is about 100,000 nanometers thick. So with our map of the terrain complete, we can finally go hunt for our atoms. All right, on to phase 2. We're going to set that thickness map aside for just a moment and turn our focus to the darkfield image. The one with all the bright, sparkly dots? This is where we're going to find the unique fingerprint that's going to let us identify each of those individual atoms. I love this detail from the research paper because it really shows you how science actually works. The raw data was messy. Their first attempt to calculate a key number was just totally unstable and bouncing all over the place. They had to figure out that they needed to carefully measure and then subtract all the background electronic noise from the image to get a clean, usable signal. And you can really see what a huge difference that made. Before correcting for noise, their calculations were basically useless. But as soon as they subtracted that noise, boom, they got a stable, consistent value that they could actually build on. It's a classic case of having to separate the signal from the noise. So this whole thing really hinges on a fundamental piece of physics. The brightness of an atom in that darkfield image is directly tied to its atomic number. We call that Z, raised to the power of about 1.7.
What does that mean? It means a heavy atom like iron with a Z of 26 is going to scatter way more electrons and shine much, much brighter than a light atom like carbon with a Z of 6. That brightness, that's our fingerprint.
But how'd they get that magic number, 1.7? They couldn't just guess. They had to calibrate their model. So they actually built a computer simulation of their sample, and they stuck known atoms, like zirconium, inside it. Then they ran a virtual microscope on the simulation to nail down the exact relationship between an atom's atomic number and how bright it should appear.
Okay, now we can finally put all the pieces together. It's really a three-step process. For any one of those bright dots, first, you measure its maximum brightness. Second, you have to subtract the brightness of the carbon it's sitting on, and that's exactly why our thickness map was so important. And finally, you take that leftover brightness, plug it into the formula, and solve for Z, the atomic number. And that tells you exactly what element you're looking at.
So, the detective work is officially done. We have our method, we've calibrated our instruments, we've cleaned up the noise. Now it's time to take this whole process and apply it to that original image of the presolar grain and finally find out the identity of those ancient atoms.
And here we are, full circle, back to our original mystery. Those bright dots aren't just random sparkles anymore. Now each one of them has a story. Each one has a specific brightness that's like a name tag, revealing its true identity from across billions of years and unimaginable distances.
And here is the verdict. The analysis showed that the heavy atoms stuck in this ancient bit of stardust have atomic numbers mostly between 18 and 30. And that range corresponds to elements we're all familiar with, things like argon, calcium, and iron. We are literally looking at the building blocks that were forged inside a star that lived and died before our solar system was even a cloud of dust.
So what's the big takeaway here? Well, this is an incredibly promising new method. Its biggest advantage is that it can identify single atoms without destroying the sample, which is a huge deal for super rare materials like this. But we have to remember, it's still a developing technique. Its accuracy depends a lot on those computer simulations, and at the time this paper was written, it hadn't been tested against a sample where they already knew what the atoms were.
But it leaves us with a truly amazing thought to end on. We're developing tools that let us read the atomic history written inside a single grain of dust from a star system that isn't ours. If we can start to do that, what other incredible secrets about how stars, planets, and maybe even life get started are just sitting out there, waiting for us to find them, hiding in plain sight?